Case now. Our next speaker is Murch. He is an assistant professor at Washington University in St. Louis. He researches AMO, which is atomic, molecular, and optical condensed matter physics. The title of his talk today is The Arrow of Time in Quantum Mechanics. And please welcome Kader.
Hi, thank you. So this is going to be a kind of a change of pace. We're going to talk a little bit about science, but also about how we're using, our quantum physics measurements to understand some of the deeper philosophical questions about our world. That is, why does time go forward? Okay, so my colleague Andrew Jordan and I have had a nice chance to sort of focus on these sort of deeper, more philosophical questions and see what our quantum experiments and experiments in general can tell us about the arrow of time. So to start with, we chose as the mascot of our research this person here, who's Janus. It's the god of beginnings and endings, passages and doorways and so forth. It's two faces, one that looks forward to the future, one that looks back toward the past. I think it's nice how the one maybe, which I think is looking to the past, looks so confused. Look at that. Yeah. But as you know, time seems to go forward, right? This has always fascinated me since I was a little kid. When we drop glasses, they break, they don't become unbroken spontaneously. You can't put Humpty Dumpty back together again so easily. And the question that many physicists ask, especially when they're getting fairly old and senile, is why does time seem to go forward? Because really it's actually a pretty good question. And it turns out that in physics we have a fancy name for this, or sort of a law that tells us why time goes forward. It's called the second law of thermodynamics. Sounds kind of fancy. What this says is that some quantity, entropy, which is kind of like heat or work or something, as a quantity of some sort, that this thing always, sort of always increases. Okay, so it's actually not a very good law. It's like more like a rule of thumb. It doesn't have to increase, but usually it does. And entropy has to do with, in some sense, how ordered or disordered something is. So the classic example, if you take a picture of my son's room, at one point it's ordered and later on is disordered. So a disordered state in some sense has more entropy. And the second law of thermodynamics says generally it's going to go from clean, tidy to disordered. And it has to do with the fact that there's more ways for it to be disordered and messy than there are for it to be clean. Okay? And you can also think that there's going to be some, it's going to take a lot of work to clean it back up. And so there's some relationship between this entropy and things like work and heat and so forth. And that's what thermodynamics is all about. So in physics, we think we have this, we at least have a rule of thumb that says, time seems to go forward, but we already knew that, of course. So, and the reason why it's a good question to ask, why does time go forward, is because our fundamental laws that describe the world, that is, the laws that describe our real world, as in Newton's laws that describe sort of classical mechanics, and even the laws that describe the microscopic world, that is quantum mechanics and Schrodinger's equation and so forth. These root laws of nature, they don't distinguish past from future. They work just as well going backwards in time as well as going forwards in time. So if you look at the fundamental rules, it's not clear why time should go forward. Okay? And just to prove that we're serious about this, I'll put some equations on the slide. These are sort of the classical equations of motion. What they really are is they sort of tell us how things propagate forward in time. So, and I can just sort of flip things around, and they work just as well going backwards and forward. So if you like, I can just replace these with play buttons, and you can press a button, and the equations of motion go forward in time, and they tell us how things fly through the air and so forth. But you can easily press rewind, and that's perfectly physically allowed. Okay, so the equations work just as well forward and backward in time. So we just sort of play the movie backwards. So my colleague Andrew, he's a theoretical physicist. So we don't let him into the laboratory to do real experiments. So when he wants to do some tests, his only recourse is to go down to the pool hall and sort of do some experiments. And so he was down in the pool hall, and he was studying this, what I just told you, that the classical equations in motion, that they sort of work the same but backwards and forwards, and he says, is this really true? Let's check. So I'll show you some movies that these are experiments Andrew did in the pool hall, trying to understand whether things really you can tell or not, okay? So here's the first movie. All right? And here's the second movie. And what I've done is I've taken one of these movies and I've played it backwards for you. And the game is to guess which one's going forward, which one's going backward. And it's kind of difficult to do because there's only one ball and it just goes across the screen. If you look really closely, you might see in one case it seems to be slowing down, in the other case it seems to be speeding up, but it might have been that it was a pool, it might have been tilted, so who knows, right? Okay, so let's do some more complicated experiments. Well, let me tell you the answer first. This one was backwards, this one was forwards. Okay, but let's make the experiments a little more interesting. Let's try two particles now, okay? So here's the first one, okay, and here's the second one. All right? Anyone want to give a guess which one's forward, which one's backwards? The first one's forwards. I think that's true. It's still kind of hard to tell, though, right? They could they're both physically allowed. They're both, allowed by the laws. Both can happen. Okay, and that's what I mean by the laws of mechanics don't distinguish past from future. They work just well going forward and backward. Okay, so let's make the experiment even more fun. Let's try three particles. Okay. Is that one? And that one, right? It's still challenging to tell, but it turns out that the first one again is forwards and the second one's backwards, okay? But as we really go to the full complexity of the pool hall, that is the pool break, it starts to become very apparent which one's playing forward, which one's playing backwards, right? So let's play. We know already what the answer is going to be. Okay, there's the pool break. Okay, and here's the other option. So in this case, it's incredibly unlikely that that's what happens in the pool hall, okay? And in some sense, just by looking at the initial condition, everything's all perfectly ordered and so forth. It's like my son's room when it's nice and clean. Here it's all messy. So in this case, we can really tell the transition, the arrow of time from the transition from order to disorder, okay? So things become more disordered, and this is, of course, what that second law of thermodynamics tells us, that, hey, look, this is your intuition. One of them is more likely to be forward than the other, and that's what it tells us. Okay, but let's look a little bit deeper, because as you know, these pool balls, if you look really closely, they're made out of atoms and molecules, right? And the microscopic world is described by a completely different kind of physics. It's described by something called quantum mechanics. So maybe all of our conclusions that we made from Andrew's videos in the pool hall are completely wrong, because we're forgetting about the fact that quantum mechanics is really what's going on at the base of what's going on. It has to do with how these particles act, okay? So let's look at quantum physics. So we know some quantum physics. In this case, the evolution of a quantum particle is governed by an equation called the Schrödinger equation. Some fancy equation up here. And it turns out that this, as I said, doesn't distinguish past from future. You could equally well play this backwards or forwards in time. Okay, so the same sort of thing applies. I can press forward or rewind on these movies. Okay? But there's something funny about quantum mechanics, kind of a quirk, which has to do with measurement. That is, in a normal macroscopic world, when you measure something, when you look to check where my water went, it's right here, it doesn't suddenly have to, there's no disturbance. It was there even when I wasn't looking at it. Looking at it doesn't change its location. That's not true in quantum mechanics. Okay? There's something strange in quantum mechanics about measurement. And you may have heard this story. So in quantum mechanics, you have something called this quantum superposition. I'll tell you more about this, okay? And when you measure it, something happens. It's called wave function collapse. It looks exactly like this. You can tell we do these experiments in St. Louis because, oh look, there's the arch. This is the whole story about Schrödinger's cat. Has anyone heard about this story? Yeah. So this is a story invented to sort of tell you how strange measurement is in quantum mechanics. Let me remind you how it goes. We created some sort of apparatus where there's a radioactive atom here. When it decays, it'll emit a photon that triggers a string to drop a hammer on a vial of poison, and this poor cat in the box will then be dead. Okay? And if we wait a period of time, so there's a 50% chance that the atom is decayed and therefore the hammer is dropped and the poison is spilled and the cat is then dead, then there'll be a 50% chance that the cat is dead. Now, quantum mechanically, the cat will then be both have a 50% chance of being alive and 50% chance of being dead. Therefore, it's both alive and dead at the same time. Okay? That sounds already kind of crazy. Okay? But the crazy thing is that when you open the box, what happens? Well, the cat will be alive or dead. You actually, by opening the box, when you force the cat to take a stand, right? You don't see zombie cats running around, thankfully. So it will be either alive or dead. And so opening the box, you either kill the cat or you bring it back to life. Okay, so the act of measurement is very strange and very sudden. Taking a cat that's both alive and dead at once to being one or the other. So measurement in quantum mechanics, maybe this does seem to sort of break this time symmetry. That is, we go from some multiple possible states, it's both alive and dead, to one or the other. That's a very asymmetric action, okay? That is, if you learn something, can you unlearn it? Okay, that's what it means to measure something. You learn something, is it possible to undo that in some way? Okay. Well, let's find out. Okay, so let's go down into my laboratory where we have a bunch of electronics. We have over here in the corner a dilution refrigerator. This is an apparatus that cools our experiments down to a hair's breadth above absolute zero. If we look inside there, we see there's lots of layers of shielding. Everything is gold-plated because gold is really pretty. And inside all this shielding, what we have is a little box, a metal box. This is half of it. It has a lid. And in this box, we put a tiny superconducting circuit. And the only thing you really need to know is this circuit has quantum energy levels. Okay, there's a higher energy level and a lower energy level. And we've got energy levels inside a box, and then it's cooled down to absolute zero and all sorts of stuff. Okay, so let's simplify the picture just a little bit. Well, you can think of it as just a box, and there's a ball, okay? And this ball can be on the bottom shelf, the lower shelf, or the upper shelf. Okay, the two energy levels of my box. This is really what we're studying. I'm just going to sort of simplify it for the sake of this discussion, okay? Now, you can't really take the ball out of the box because it describes what state the circuit's in. So it's either this one or this one in some sense. Okay. Now I'm going to let you see inside the box, but we're actually going to do the experiments with the lid closed on the box. And what we'll do is we'll do some experiments, then we'll open up the box and see what shelf the ball is on. Okay? And the way this works is there's some sort of peculiar rules for what happens. So the first thing is, if we send in a pulse of energy with just the right length and just the right height, we find that we can move the ball from the bottom shelf to the top shelf 100% of the time. So we put the ball on the bottom shelf, close the door, send in the pulse, always on the top. We'll do it over and over again. It's always on the top shelf. Okay? Now, if it's on the top shelf and we send in that pulse of energy, it moves it to the bottom shelf with 100% probability. Okay? So we can check that again. Put it on the top shelf, send in the pulse. It's always on the bottom shelf. Now, the question I want to ask is what happens if we send in a half pulse? And I don't mean it has to have this funny shape. It's just a pulse that's half as long or half as much amplitude. It's not quite enough energy to get at the top shelf. Okay? Well, what we find is we send it in, and half the time when we open up, it's on the top shelf. And half the time we open up, it's on the bottom shelf. I didn't actually cut it in half. I'm just showing that 50% of the time it's top shelf, 50% of the time it's bottom shelf. Okay? Now, you could say, oh, it's a 50% probability that it works. It's just working half of the time, right? That's actually not the case. It's something much deeper than that. And let me prove that to you by way of a counterexample. So if it was only 50% probability of exciting to the top shelf, then what would happen if we send in two of these pulses? Okay? Let's think through this. The first pulse is going to move the ball from the bottom shelf to the top shelf with 50% probability, right? Okay, now, so maybe it's on the top, maybe it's on the bottom. We send in the second pulse. If it's on the top, it goes to the bottom half of the time. If it's on the bottom, it goes to the top half the time. So there should be no effect from the second pulse, right? And that's not what we see at all. What we see is if we send in 2 of these pulses, it moves the ball to the top shelf with 100% probability. Okay, so a half plus a half is a whole. That's not too surprising, but there's we're waiting in between here. So what does that mean? It has to somehow remember that we sent in that first pulse. Okay, so the only conclusion is that there's some sort of shelf in between. Okay, some sort of stable state that's both the top shelf and the bottom shelf. And after we send in this first pulse, it's on that shelf. Okay, this is what a quantum superposition is. It's in a quantum superposition between the bottom shelf and the top shelf. There really are only 2 real shelves. But when you send in this half pulse, it can be in both shelves at once, and therefore it's ready to go the rest of the way with a second pulse. Pretty amazing. Turns out if I send in, say, a half pulse of negative amplitude, I can make a different kind of one of these superposition states. In fact, I can send in a 3/4 pulse or a 1/4 pulse. All of those create sort of different stable shelves, different superposition states between top and bottom shelf. So I can kind of think of it as a circle, infinitely many possibilities. This is part of the reason people are excited about quantum mechanics for a computer, because instead of just one or the other, it's any possible combination of those 2. So this is what we call a wave function. In quantum mechanics, we give it a Greek letter because Greek letters are cool. And it's some combination of top and bottom. Any combination I want to write is allowed. Okay, and I can just create those by sending in different pulses. But what happens when you open up the box? Okay, there are only 2 real shelves, so it's like the cat has to be alive or dead. Okay, so the ball will be on one shelf or the other. So I told you it was on both shelves at once, but we open the box, it has to choose top shelf or bottom shelf. And this is a part of quantum mechanics which is fundamentally random. Okay. And this is something that bothered Einstein to no end. He said, God doesn't play dice with the universe. But it turns out that in quantum mechanics, really this is fundamentally random. That when you open the box, it's a truly random event, top shelf or bottom shelf. Okay? What I want to get, and that's, of course, the collapse of the wave function that I talked at the beginning. It's in this beautiful superposition, both shelves at once. We open the box, it has to be one or the other. I want to ask, can we do this in a more gentle way? Can we open the box ever so slowly to see how it, just peek in there, and to see how it chooses what shelf it's going to be on. Okay, and that's what we're going to do. So here we are. After we send in this first half pulse, there's a 50% chance on the top, 50% chance on the bottom, but we know it's in this stable state in between, the superposition state. So we have no predictive power for what shelf it's going to be on. We could just flip a coin if we want. So let's do a more careful experiment. And this experiment is going to involve lasers, because of course lasers are cool. And so what we're going to do is a tiny little hole in the box over here, and a tiny little hole over here. We're going to send a very dim laser beam through, and we're going to count the photons that come through on a detector. Okay? So to understand how this works, first we'll put the ball on the bottom shelf, and we'll send the laser through, and we count photons, and we count them. 3 photons, 2 photons, 1 photon, 1 photon, 5 photons. We don't get the same number of photons because, well, photons are quantum particles too, and they also have fundamental randomness. So they don't come in a neat order one after another, but they kind of randomly distribute themselves. And so we get what we call shot noise. It's just the photons and numbers, the number of photons is not very steady, okay? For a fundamentally quantum reason. So if we want to see, we get a distribution of photons. On average, there are 3. Sometimes there are 0. Sometimes there are 5. That kind of tells us how many photons we get, what the probability of getting a certain number of photons is. Okay, so now let's put the ball on the top shelf, and we see, we got 5 photons, 4 photons, 2 photons, 1 photon. We got on average more photons. So you can think maybe when it's on the bottom shelf, it's blocking the laser beam a little bit. Top shelf is not blocking it as much. So now we get more photons than average, but again, because of the fluctuations, sometimes we get as few as 3, sometimes we get as many as 9. Okay? So this is the measurement we're going to do. This is how we're scientifically peeking into the box. So now back to our question. We've created this superposition state, this top shelf and bottom shelf at the same time, and we're going to peek into the box by sending in this very dim laser beam. Okay, and so let's do it, and we'll count the first bit of photons, and we get 7 photons. Okay, so what do you think? 7 photons. If you had to guess whether when we open the box, if it ends up being on the top shelf or the bottom shelf, what would you guess in this case? That is the red shelf or the blue shelf? The red shelf. Well, why is that? Well, it's because, it's much more likely that you'd get 7 photons if it happened to be on the red shelf. Okay? And that bit of logic that is so intuitive has a fancy name. It's called Bayes' theorem, developed by Thomas Bayes back in the 1700s. It says the probability of A given B is the probability of B given A times the probability of A divided by the probability of B. Kind of a nice mantra of A's and B's. The idea is that if you think of A as some new information, or think of B as some new data, then what can that say about the odds of A happening? It's kind of hard to think through in the form of a formula, so let me give you an example. Let's imagine that it's nighttime, okay? And we want to know, did the sun just explode? It's not something I normally worry about, but it's a nice example. The idea is we have a neutrino detector, and the neutrino detector can measure neutrinos that are coming from the sun, and it can tell if the sun's still burning. The point is, neutrinos interact so weakly with matter, they come right through the Earth when the sun's on the other side, they come right through the roof when the sun's up. So the neutrinos don't care whether or not the sun's set. We can tell whether or not the neutrinos are coming from the sun, and whether or not it's exploded or not, okay? But this is a very funny detector, because after it measures the neutrino flux, it rolls 2 dice, and if they both come up 6s, it lies to us. And if they don't, it tells the truth, right? So we press the button and it says, yes, the sun has gone supernova. Okay, so it's hard to know because we don't know if it's lying or not, so we have to analyze this with statistics. Okay, so there's 2 ways to do this. Standard statistics would say, what is the probability that this event happens by chance? Okay, so that's 1 in 36. Chance you get double 6s in which it's lying to us. That's like 2.7%. In statistics lingo, that's a p-value less than 0.05. That means it's a conclusive result that yes, the sun has exploded. And the Bayesian statistician says that's ridiculous, because Bayes statistics are really just common sense. But so what calculation did this Bayesian statistician do? What's the following? The probability of a supernova given the yes answer is the probability of a yes answer given the supernova. We actually know what that is. That's the probability that the detector didn't lie to us. It's 35 over 36, about 97%. Then it says, okay, we have to multiply that by the probability of a supernova. Anyone know what that probability is? Small. Maybe 0? Is that a good? Yeah, about 0. So even my son can do this math here. So 97% times 0 is 0. So yeah, the probability of the supernova is 0. The point is back to this problem here. Now, when we apply Bayes' rule, we have the probability of the bottom given n photons. We want to know what the probability that's on the bottom shelf. That has to do with the probability that's on the bottom shelf originally, that's a half, times the probability of n photons given the bottom shelf. And that's exactly what this distribution tells me. Okay, so we can exactly apply this logic to update our knowledge of what shelf it's on as we collect photons. Okay, so here's how it works. Since I can have infinitely many states here, let me just replace these clumsy balls with an arrow that points to where it is. So it points up, it's on the top shelf, points down, it's on the bottom shelf, when it's side, it's in the superposition state. Okay, so we'll start here, and we'll start detecting photons. We detect 6 photons, it means it's more likely to be on the top shelf. 0 photons, more likely to be on the bottom shelf. We're not sure, because you could still get 0 photons if it happened to be on the top shelf. So it hasn't gone all the way down, but it's kind of tilting down. Then 3 photons and so forth and so on. We can see how the state evolves. That is our state of knowledge as we collect the photons, okay? So we have a movie now of how the quantum system's evolving as we peek into the box, okay? And this movie is what we call a quantum trajectory. And just to prove you that these are really kind of the experiments we do, here's some experimental data. So I prepared this top shelf plus bottom shelf. And then each of these colored traces is a different run of the experiment as I count photons. Okay? And you can see, here, this one goes up to the top shelf. This one goes down to the bottom shelf. This one kind of wanders around and never quite sure what shelf it's on. So forth and so on. So these are movies of wave function collapse. So now we can look into the box ever so slowly. And some funny things happen here. So if we go back to this example here, what we saw is we see 6 photons goes up, 0 photons goes down, 3 photons goes back to where it started. So we were peeking in the box. We peeked in there for 3 instants of time, and we didn't learn anything. In some sense, the measurement started to go up, started to go down, and then it reversed itself. Okay? So the measurements themselves can be reversible. They can undo themselves. You can kind of have information that cancels out what you learned before. So it is, in some sense, possible to forget something or to unlearn it. Okay, so that's what we call a measurement reversal. And you can see that in our experimental data. Here's this blue trace, goes up, and it goes down, and it goes up, and it goes down, and it's back to where it started. Okay, so we measured it for this long, and the measurement reversed to where it started. Okay? So here's a kind of an even better drawing of that. Here's one of these. Here's the number of photons in blue as a function of time. Here's the state here, what shelf it's on. So it goes up to the top shelf. The question is, could you play this movie backwards in time? And the answer is yes. If we started up here, then in order for it to go backward in time, the number of photons would have to be just you take the record of photons, you flip it upside down and backwards, it exactly causes us to go backwards. So all we have to do is flip the record of photons backwards, and the movies play in reverse. Okay? So it's like a movie with a soundtrack. It only plays backwards if you also flip the soundtrack to go backwards and upside down. Okay, so this is back to our game of watching the pool in the pool hall, right? If we watch these movies, can we guess which one is more likely to be going forward in time or backward in time? That was easy to do in the case of classical mechanics. Can we do this now in the quantum case? Okay, and we can actually be a little more precise, because I can actually tell you the probability of a particular movie going forward in time or backward in time. But I'll try to explain that now. So here's our state. At this point, it's equally likely it's in the bottom shelf or the top shelf. And so for simplicity, I'll just replace this distribution with one distribution that looks like this. Okay? If I add the two together, that's what I get. All right, if I detect 6 photons, that 6 photons was over here in the distribution. Okay? So you can think about the probability of detecting that photon, or the probability density. It's not the most likely thing, but it's over here. Okay? After I detect that, it's now more likely to be in the top shelf. So these distributions have different weightings, and that causes this to shift over. Okay? If I detect this 0 photons, that was over here, and now that happens with a certain probability. So I can multiply together these probabilities to determine the probability of a specific movie. Okay? Now I can think about what it would take to reverse a trajectory. So here's one that's fairly likely. If we detect that many photons, it goes now up toward the top shelf. That causes the distribution to move over. Then if we detect that many photons, it reinforces what we already learned, causing it to move over further. And then if we can detect that many photons, eventually we become very sure that it's on the top shelf. That's a collapse of a wave function, but slowed down into this sort of peeking in the box movie. Now we can reverse that process. What we have to do is we have to detect very few photons, something that says, you know what, really, it should actually be on the bottom shelf. But that's very unlikely. And so in order to reverse this trajectory, we have to get very unlikely results over and over again to kind of to change my thinking about what state it's on. Okay? And that's similar to this story about the bedroom, that there's many ways for it to be messy. There's lots of ways for it to go forward. There's kind of fewer ways for it to be clean. Okay, the same sort of probabilistic story. So let's be a little more quantitative about this. So if I look at one of these trajectories, I can go ahead and I can determine what the probability density of each one of these points is, multiplying them all together, and I get something that's like 10 to the minus 300. So that's kind of unlikely. If I think about the reverse process, though, the probability of that is 10 to the minus 310. So while both of them are incredibly unlikely, the reverse process is less likely than the forward process. Okay, so we've done some experiments. Here's what we see. What I'm showing is the log of the forward probability divided by the backward probability. Basically, if this is positive, greater than 0, that means it's more likely to be going forward in time. And if it's less than 0, it's more likely to be going backward in time. And we've done the experiment many, many times, and so what we see is that 500 times we got something here like this, where this ratio is positive. That means that the movie was more likely to be going forward in time. Okay, but the red pieces indicate that sometimes we watch these movies, and they happen to be more likely to be going backwards in time. Okay? So we have, every once in a while, these collapsed movies we make are going backwards in time in some sense, or they're more likely to be going backwards in time, but on average, they're more likely to be going forward in time. Again, that's connected to the second law of thermodynamics. Entropy sort of always increases, but it doesn't necessarily always have to. That's kind of what we're seeing here. So let me summarize what I've told you. Okay, so we first talked about how classical physics is time reversible, right? We can play these equations backwards and forth. It's hard to tell which way those movies of the balls are going. Okay? But when we have enough degrees of freedom or enough particles, we can tell the past from the future by the transition from order to disorder. Okay? That's the second law of thermodynamics. Now, quantum physics is also time reversible. That is, a Schrodinger equation can be played forward and backward in time. It's the same sort of equations as classical mechanics, except for when it's not, which is the case of this wave function collapse. Okay, this is very much a forward in time type of thing. This wave function collapse breaks this symmetry. But quantum measurement can also be time reversible. That is, if we measure things weakly, then we can find that they go backwards. They can be reversed. So we can make it reversible again, but we can still tell the past from the future as we make the transition from disorder to order, as we learn more about the system. Okay? So it's not exactly the same story as in classical physics. Here we're going from disorder. Here we're going from disorder to order. We're learning more about the system, and it's that acquisition of knowledge that's sort of telling us the arrow of time. But in both cases, we have a probabilistic arrow of time that emerges when we watch these movies. So with that, I want to conclude. When we started this project, well, I was looking at these movies and I was like, wow, time is just really symmetric. And we've been working on the symmetry, and I thought, we'll do this research, we'll find that, you know what, time is actually perfectly symmetric, and you can't tell the past from the future. Sometimes you do the research and then actually find out that your initial hypothesis was wrong. That's the most exciting case. That's what we found in this case, that really as we watch these movies, we can tell probabilistically which way time is going. And this is sort of course, that's reassuring because time does seem to go forward. So I want to acknowledge Andrew Jordan and my colleague here who's helped with this research, helped think of the ideas, and my research group, the folks that do all the work and so forth, and various funding agencies that pay for all of the equipment in our time. So with that, I'll thank you for your time. And look for questions.
All right. So, if I understand correctly, you're saying that you can imply or infer the movement of time based on order or disorder. Where does work come into that? I mean, for instance, if you have the picture of the disordered room and the ordered room, but somebody has done the work of cleaning the room, how does that fit into, whether that's, human intentional work or just energy going into a system?
So let me say that indeed it takes some work to prepare initial states to start out in a specific configuration. So in fact, when we prepare the superposition state, we have to do some work to get it into that specific state. Okay. Indeed, you have to do work to get the room clean, okay? And in some sense, going back to the thermodynamics, the work I do to make the room clean, I have to eat some food, and so I'm making a lot of disorder in terms of turning bananas into digested solids and so forth. So I'm only making a subsection of the room less ordered. So overall, entropy generally increases. There's also a relationship to work for these you can think about, is there work associated with the quantum measurement? Is there heat associated with quantum measurement? What kind of energy is it? Okay, and it turns out we claim that it's just the heat. It's all sort of heat when we do work to prepare the superposition state, but then whether it goes to the top shelf or the bottom shelf, that form of energy change is a type of heat. Okay, so that's, I don't know if that answers your question, but that's more or less.
So you can't show slides to a bunch of atheists with the John Templeton Foundation without some explanation of why are they funding you?
That's an excellent question. And that's in some sense why I'm here. They're interested in funding big questions, and the arrow of time is a big question. Okay, the intrinsic randomness of quantum measurements, and has to do with the notion of determinism and so forth. And these are questions that they're interested in finding out answers to. They may not be the answers they're after, but they're the answers that we're seeking. So it's my goal to present our findings to everybody about these things, and so I think it's suiting perhaps to present these findings here, and I think that they're of interest to everybody. So.
Hi, Cater. Thanks for the talk. So you work with a lot of analogies here and stuff, and I have more questions than anything now that you've spoken. I just want to know, when you're talking about this, what do you mean by time? And when you open the box, what do you mean when you open the box? What occurs when you open the box?
Yes. So time is time I measure on my clock and so forth. It's the thing that the clock ticks forward when I'm talking about these experiments. And when I say open the box, it's me slowly accumulating information about the system. So the experiments don't actually use balls in a box and so forth. They don't even actually use lasers per se, but the essence is true. I'm slowly sending light into the system. The light that comes through carries lots of fluctuations, and I'm asking, what did I learn from that light? What can I check? What can I know about the system? What can I predict about it, given what I learned? And that's what I mean by opening the box. Okay. And so our research has allowed us to take this original notion of you open the box and the cat is alive or dead instantly, this wave function collapse all at once, and to slow that process down and to look inside wave function collapse. And originally, or many people attributed this wave function collapse to the origin of the arrow of time, that in quantum measurement, you have this irreversible process, time must be going forward. And our research showed that actually you don't need wave function collapse so much, you can slow that down, we can look at the dynamics, and it actually turns out that in those dynamics, there is a probabilistic arrow of time that emerges in a very similar way to we have in classical mechanics.
One comment on it. So I think time is the way we put on change. So it's not really a thing. So really what we're talking about is change entropy.
So the question is that time really has to do with change, and yes, that's true. So we talk about how, looking at these histograms and so forth, the strength of that correlation, it has to do with the ratio of time over some characteristic time scale. So really it has to do with how much information we've acquired. So if you like, the measure of time could just be net information. Okay, so in some sense, the actual ticking of seconds doesn't matter so much. I can just send in more laser power and make the whole thing go faster. So the actual duration doesn't matter so much. It has to do with the rate of information accumulation that sets the overall scale of this. So I think that probably follows your intuition in terms of how much change there is.
I had a question dealing with the research going into describing or explaining the origins of the universe. Is this line of research conducive to this as well, to that topic? Discovering decay in particles and such like that?
There are some, I think yes. although maybe not particularly directly. The notions of probability and entropy are like, what is the likelihood that our universe came from the Big Bang, a very low entropy initial condition, versus that our universe arising out of a very high entropy state, and that it just sort of happened to fluctuate into this universe that we currently have. The notions of probability and entropy play a big role in those sort of fundamental philosophical questions. And if you think about it long enough, it's actually very surprising in some sense that our universe started in this very special low entropy state at the Big Bang. It's actually kind of surprising that that happened. Probabilistically, it might be more likely that it started in a higher entropy state, and that we're kind of, living in one of these branches where things just became low entropy by accident in some sense. So, yes, these ideas do play into the origin of the universe. I'll give you that.
We can take one more question.
I always hope I'm not asking a dumb question. From what I'm kind of understanding with the decomposition of the superpositions, not the collapses, but the one where you're slowly looking at it, one way in which you can think about it is that you can tell time's going forward as opposed to backwards because the events are feeding back upon themselves?
Yes. Excellent point. So, there are no stupid questions, there are only stupid answers. Indeed, that's exactly what's going on, and this is something we want to understand, but you could see that the information changes the state, and therefore it reinforces itself, and this is what drives this collapse process to go to one or the other, and not just sort of diffuse around forever. Okay? And it's because the information changes the state, but the state also gives you the sort of the information, you have feedback or something, and this is maybe, there's some fancy words for it, measurement back action, that sort of reinforce what you've seen before. And that makes the reverse very unlikely. And that is why we have overwhelmingly more likely to be going forward in time, indeed. So there's some feature of the measurement system that's leading to that. And that's something we'd love to understand more deeply. That's kind of why we're doing this research. So, great question.
Thank you, Kader. Can we have a round of applause?